So the last talk will be by Ed Witten, who will be telling us about the background-independent algebra in quantum gravity.
Well, thank you, Juan, and thanks to all the organizers of the conference. Can you all hear me in the back? Okay, so Juan has just mentioned my title, so I won't repeat it. In an open universe, we're familiar with the fact that in the presence of gravity, for example, in an asymptotically flat or asymptotically anti-de Sitter spacetime, we can define asymptotic operators. For instance, the boundary operators in an asymptotically ADS spacetime. That basically means that we can take the point of view of someone who looks at the spacetime from outside and characterize it by those asymptotic observables. But what can we say about a closed universe? That means a universe where the spatial sections are closed. Well, we can always quantize the classical phase space of the theory and define a Hilbert space. And once we have a Hilbert space, there are operators that act on it. The only question is what those operators mean. Unless you're interested in the viewpoint of someone who can look at spacetime from the outside, it's hard to imagine an answer unless the operators we define are supposed to be measurable by somebody in the spacetime. But if you give that answer, you immediately have to ask, who's the someone who's supposed to make the observations? In a closed universe, in general, there are cosmological horizons. Different observers can measure different operators. To say anything, we should pick a particular observer and discuss the operators that that observer can measure. Now, in trying to do this, I'm going to aim for background independence. By background independence, I mean I'll define an algebra that depends on the laws of nature, but doesn't depend on the space-time the observer is living in. So for example, if the assumed theory is 11-dimensional M theory, the algebra will not depend on where we are in the landscape or on the topology of space-time, assuming we're on a space-time that can be described by 11-dimensional supergravity. It will depend upon not just 11-dimensional supergravity, but it's, in principle, it's M theory extension. If there are heavy operators that the observer can ultimately measure that aren't present in the low energy theory. Different spacetimes are going to correspond to different representations of the same algebra. We'll see that by proceeding in this way, we can get a better understanding of at least some aspects of what entropy means in cosmology. Now, why would one hope for background independence in the strong sense I asserted? I think it's the analog of what we usually do without gravity. So in ordinary quantum field theory, one thing we do, for example, is that for an open set U, we define an algebra AU. And this algebra has the property that it does not depend on the state of the quantum fields. The operators in the algebra act on the quantum fields, but the algebra is defined universally. It depends on U, but it doesn't depend on the state of the quantum fields. But in gravity, the space-time is part of what the quantum fields determine. So the analog in gravity would have to be an algebra that doesn't depend on the space-time. Now, following many previous authors, I'll model an observer by a time-like worldline gamma, which I'll take to be a geodesic. And I'll assume that what the observer can measure are the quantum fields along the worldline, which make up an algebra that I'll call A of gamma. So I'll be describing this paper I've indicated here, but here's some earlier works, although I won't have time to explain very much about what's in them. I will just say that I'll be explaining a construction in this paper from a different point of view. Well, why are we entitled to introduce an observer? That's one basic question we should ask. We expect that in a full theory of quantum gravity, an observer cannot be introduced from outside, but must be described by the theory. For example, we are cosmological observers, and we believe that we are described by the theory that we're trying to understand as physicists. So we can't introduce an observer external to the theory, just as we can't introduce an observer external to the space-time, at least not in a closed universe. What it means to assume the presence of an observer is that we consider a space of states in which an observer is present, and we try to define operators that make sense in that space. We don't try to define operators that make sense in all states. Abstractly, we could try to define them as operators on the full Hilbert space of the theory. We just wouldn't have a good physical interpretation for them. Well, first let's describe the algebra along the observer's world line in the absence of gravity. The observer propagates in a space-time M on a time-like curve gamma. When I get to gravity, it will be important to have a dynamical principle for the world line, and the simplest is to assume it's geodesic. But in the absence of gravity, we could consider any time-like curve. The world line is parameterized by proper time tau. The observer measures along gamma, for example, a scalar field phi or the electromagnetic field F mu or the Riemann tensor, and their covariant derivatives in normal directions. Let's focus on a particular observable. Say phi of x of tau for a scalar field phi, where x of tau is the position of the observer at proper time tau. I'll abbreviate that simply as phi of tau rather than phi of x of tau. When we take gravity to be dynamical, we have to consider that the same world line can be embedded in a given space-time in different ways, shifting tau by a constant. So with gravity, we want to impose diffeomorphism symmetry. When we postulate the existence of an observer characterized by a world line, we don't have to worry about diffeomorphisms that move that world line, and we can consider only symmetries that keep its intrinsic geometry fixed. But a constant shift of the proper time is an important symmetry of the picture. So phi of tau isn't a meaningful observable because we wouldn't know what's meant by tau. Without gravity, there's still an arbitrary zero of tau, but without gravity, we include phi of tau for all possible taus as operators in the observer algebra. With gravity, none of them are good operators. To get something reasonable, we have to introduce the observer's degree of freedom and define tau relative to the clock carried by the observer. Now, in a realistic model, we'd want to equip the observer with a battery that powers experimental equipment, a recording device to record the results of observations, and perhaps a brain to think about it. But for today's purposes, where we only will aim to understand entropy, all we're really going to care about is the observer's energy. So we'll give the observer a Hamiltonian, H observer, which I'll take to be a constant mc squared, the mass of the observer, plus a variable q, which is the excess energy above the observer's ground state. And it turns out that we should assume the observer energy is bounded below. So we'll take q to be non-negative, and then m is indeed the observer's rest mass. Then we only allow operators that preserve the condition that q is non-negative. So for example, if p is conjugate to q, the operator e to the minus ip is not a good operator because it doesn't preserve the positivity of q. But we can turn any operator into a good operator by acting before and after with what I'll call pi equals theta of q, the projection operator onto non-negative q. So e to the minus ip is not a good operator, but pi e to the minus ip pi is a good operator. It's not unitary, but it's a good operator in this Hilbert space. Now, we only want to allow operators that commute with the diffeomorphism that moves the observer forward, proper time forward. That operator is a sum of the observer Hamiltonian plus a bulk, the generator of a bulk diffeomorphism that generates proper time shifts along the world line. I didn't tell you what H bulk does away from the world line. It doesn't matter because diffeomorphism generators that are trivial along the observer world line will be set to 0 as constraints anyway. So any H bulk that generates a shift that maps the observer world line to itself, shifting the proper time by constant, will be equivalent to any other here. We just take H bulk to be any gravitational constraint operator that generates a shift in tau along the world line. So an operator that commutes with H hat is invariant under a space-time diffeomorphism that moves the observer world line forward in time together with time translating the observer system. So we want to impose that as a constraint and only to allow operators that commute with that constraint. Well, how do we find operators that commute with this constraint? Well, since H bulk is generating shifts of the proper time. It does this. So we need, with H observer is a constant plus Q. So we need Q to do this with a plus sign. And since P is minus I d by dq, we can achieve that by replacing tau by P. So Q and P being conjugate means that Q is I d by dP. So Q is generating constant shifts of P. And therefore, if I consider not the operator 5 tau, but 5P, Q acting on 5P will generate shifts that will just cancel this. More generally, we could set tau to be P plus S. So a typical allowed operator is 5P plus S, except that we have to remember that isn't quite allowed because it would not preserve the condition that Q is non-negative. So instead, we should take pi times 5P plus S times pi. I'll call that phi hat sub S. That's a typical good operator along the observer's world line. In addition to these operators, with phi possibly replaced by any local field along the world line, such as the electromagnetic tensor or field or the Riemann tensor, there's one more obvious operator that commutes with the constraint, namely Q itself. So we define an algebra A sub observer that's generated by the phi hat S as well as Q. Now, hopefully what I've described sounds background independent, since we described it without picking a background. But background independence really depends on interpreting the formulas properly. We won't get background independence if we interpret phi hat S and Q as Hilbert space operators. To get a Hilbert space in which they act, we'd have to pick a spacetime M in which the observer is propagating. Then we won't have background independence. We'll get a representation of the algebra, but it will depend on M. Concretely, the way it will depend on M is that there are a lot of relations among these operators that are not true universally. They depend on M. And if we pick an M, a lot of operators will drop out of the algebra. It'll become much smaller. And the quotient by a big ideal will act on the Hilbert space of M. But that ideal will depend on M. So what we get when we have a spacetime will be a representation of the algebra, but it will be a representation that depends on M. So since we don't have Hilbert space operators till we have a Hilbert space, which we don't have until we have a spacetime, we will not have background independence here if we think that the symbols I've written, like Q and phi hat S, are Hilbert space operators. We have to interpret them differently. To get background independence, we have to think of the observer algebra A sub observer as an operator product algebra rather than an algebra of Hilbert space operators. The algebras for different M's, as I've said, will then give inequivalent representations of the same underlying operator product algebra. To make this a little more concrete, in the absence of gravity, so what I said is also true in the absence of gravity, and in the absence of gravity, although the algebra will depend, well, in the absence of gravity, we'd characterize the objects 5 tau by universal short distance singularities. And if we describe it that way, and if we include the Riemann tensor, which in the absence of gravity is a C number, but if we allow the coefficients in the OP to depend on the Riemann tensor and its covariant derivatives, then the OP is universal. So in the absence of gravity, we could define a universal OPE algebra along the observer world line. But of course, it would not be a Hilbert space operator algebra. To turn these symbols into Hilbert spaces, we need to embed the world line in an actual space-time and construct a Hilbert space that they can then act on. So this characterization of the OP algebra doesn't require any knowledge of the quantum state. That's why OPEs are useful. For example, in QCD, where we don't understand the quantum states very well, we still understand the OPEs of operators. And that's useful because we can make some experimental predictions that don't require understanding the quantum states. After coupling to gravity and including the observer and the constraint, the short distance expansion in powers of tau minus tau prime becomes an expansion in 1 over Q. I won't quite have time to explain this, but the usual short distance singularity is regularized in this construction by gravity, so that you don't get short distance singularities, but you do get asymptotic expansions in powers of 1 over q. So we characterize the observer algebra purely by the universal short distance or 1 over q expansion of operator products. And with that understanding, the observer algebra is background independent. Now, as I've actually already said, if M is any space-time in which the observer is found, and H is the Hilbert space that describes the fields in M together with the observer, then H provides a representation of the observer algebra, A sub observer. There's a very special case that turned out to be important. And this case was originally analyzed in the CLPW paper that I mentioned before from a different point of view. That's the case that M is an empty de Sitter space with some positive value of the effective cosmological constant. In D dimensions, the metric is this one, where d omega squared is the metric of a round sphere with unit radius. At time t, the sphere has radius r cos t, so it grows exponentially toward either the past or the future. The space-time can be described by a Penrose diagram, which I hope is fairly familiar. Time runs vertically. The blue lines are the infinite future and the infinite past. The left and right edges of the diagram correspond to the north and south poles of this unit sphere. And they're both geodesics. And using the symmetries of de Sitter space, I can assume that the observer geodesic is the left edge. And then sketched in green is the part of the space-time that the observer can both see and influence. That part is bounded by a future horizon and also a past horizon. And the green region is called a static patch because there's a particular de Sitter generator, H, that advances the proper time of the observer, moving the observer forward in time. Since it maps the observer world line to itself, it inevitably maps the green region to itself because the green region is causally related to the observer world line, and a de Sitter symmetry preserves those causal relations. So as it maps the world line to itself, it maps the green region to itself. And we can think of this de Sitter generator as the operator which I called H bulk before, which is a constraint operator that moves the observer world line forward in time. In a generic space-time, there was no canonical choice of H bulk, but in empty de Sitter space, there is. Now, in the absence of gravity, there's a distinguished de Sitter state. It's often called the Bunch-Davy state. I will just call it psi sub ds, which can be defined by analytic continuation from Euclidean space. And Euclidean space is a sphere, in this case. So the boost symmetry of de Sitter space generated by what I called H becomes a rotation symmetry of the sphere. And that leads to a thermal interpretation of correlation functions in the state psi ds. Correlators in the state psi ds are thermal at the de Sitter temperature, which I'll call TDS. It's 1 over beta ds, where actually beta ds is the radius that I had on the last, 2 pi times the radius I had on the last page. Now, what exactly does it mean to say that correlation functions are thermal at the de Sitter temperature? Thermality of correlation functions means 2 key properties. The more obvious one is time translation symmetry. If you consider a 2-point function of operators at times tau and tau prime, you can shift them both by constants, a common constant s. And that's an invariance. But of course, that condition is much, much weaker than time translation symmetry. It just describes any time independent state. Sorry, that condition is much weaker than thermality. I think that isn't what I said. It describes any time independent state. Thermality is captured by the KMS condition. So in quantum theory, operators don't commute. So if I look at a 2-point function, I can't just reverse the order of the 2 operators. And in general, there's no relation between excitation values of A times B or of B times A. But a thermal ensemble has the property that if you exchange the 2 operators and also shift the time by minus I beta, then you get an invariance. So that's the KMS condition, which says that the correlators are thermal. And the assertion that correlators in the state psi ds are thermal is equivalent to these two assertions, or these two plus the generalization to endpoint functions, or the statement that the state psi ds has thermal excitation values. Now, including gravity in the observer, we define a special state in which the observer energy has a thermal distribution at the de Sitter temperature. I'll call the state psi max for a reason you'll see shortly. And it's simply psi ds times an exponential function of q, which is arranged so that the energy distribution is psi squared. And so I've chosen this function so that psi squared is e to the minus beta q, which is a thermal distribution of the observer energy q. And I've included a normalization factor, which is the square root of beta. So including gravity in the observer, we replace the de Sitter state by this extended version, which is a thermal state now, but including the observer. And we replace 5 tau by the gravitationally just operators I told you about before. And now a straightforward computation shows that the two facts on the previous page, these two facts, have generalizations. The obvious one is the generalization of time translation symmetry, which is that now we can shift the arguments s and s prime by a common constant c. Less obvious and much deeper is that the KMS condition simplifies. There's still a version of the KMS condition, but now it's the naive statement that the two operators can be exchanged. We no longer have to make the shift of minus I beta. The first statement is fairly obvious, and the second one has a short contour deformation proof, though I reluctantly decided not to show it today for time. So the second condition tells us that if for any operator A in the observer algebra, we define the expectation value in the state psi max to be what I call trace A, then the trace does have the algebraic property of a trace. The trace of AB is the trace of BA, because, as I said here, for expectations in psi max, you can exchange the two operators. So therefore, if I call the 2-point function in the state psi max a trace, the second condition is just the tracial property of that function. It's also true that the trace of A dagger A is positive for all non-zero A. So in particular, the trace is non-degenerate, meaning that for any A, there's some B such that the trace of AB is non-zero. Namely, we can take B to be A dagger. Another fact is that if psi max is normalized, which I actually did, to be a unit vector, then the trace of the identity is 1. Now, although trace has the algebraic properties of a trace, it's not actually a trace in any representation of the algebra A sub observer. We do have a Hilbert space representation of the algebra, namely at X1, the Hilbert space that describes quantum fields in de Sitter space tensored with functions of Q. But the trace of an element of the algebra in this Hilbert space is infinite. The operation I've denoted as the trace is a sort of renormalized trace with an infinite factor removed. Now let psi be any state in the Hilbert space. I should have said the extended Hilbert space, including the observer, not the original one. And consider the function that takes an operator A in the algebra to its expectation in the state psi. Well, that's a linear function on the algebra. But the algebra has a non-degenerate trace. And the non-degeneracy means that for any psi, there is a corresponding density matrix rho in the algebra, such that the expectation value of A in the state psi is the trace of A times rho. So rather, as in ordinary quantum mechanics, rho is a positive element of the algebra whose trace is 1. And it's also easy to show that any such positive element is the density matrix of some state. So for measurements that can be made by the observer, the state psi can be replaced by the density matrix rho, and you can forget about all operators that aren't in the observer algebra. This trace is just a function on the observer algebra. And so any measurements made by the observer require only a knowledge of the density matrix, exactly as in ordinary quantum mechanics. For example, let's find the density matrix of the state psi max. Well, The definition of the trace of A times sigma max is going to be the density matrix of psi max. The definition is that the trace is the expectation in the state psi max. Now, for sigma max to be the density matrix of psi max, it's supposed to obey this property. But comparing that property to the definition of the trace, we see that we simply want sigma max equals 1. So the density matrix of the state that I called psi max is the identity operator. Well, that means intuitively that psi max is maximally mixed, similar to a maximally mixed state in ordinary quantum mechanics, whose density matrix is a multiple of the identity. Now, once we pick a space-time the observer lives in, elements of the observer algebra become Hilbert space operators. As I said before, they obey a lot of relations that they didn't obey universally, and the observer algebra becomes a von Neumann algebra. For our purposes, a von Neumann algebra is just an algebra of Hilbert space operators. We'll forget any further technicalities. But basic properties of the algebra, including what's called its type, depend on the assumed spacetime. In fact, in the example I've been describing of empty de Sitter space, the algebra obtained this way is of type 2-1, as follows from the existence and properties of the trace. So that was explained in much more detail in this paper. That contrasts with what happens in ordinary quantum field theory. In quantum field theory without gravity, if you take a region U, the corresponding algebra A sub U is of type 3 as discovered by Araki. And for today, all we care about is that a type 3 algebra doesn't have a trace, and therefore it also doesn't have density matrices. So technically, there's no proper notion of a density matrix or a trace for a local region in ordinary quantum field theory. Concretely, you will run into ultraviolet divergences if you try to define such density matrices and entropies. So instead, at least for the example of the static patch of de Sitter space, we've learned that including gravity turns the algebra into the somewhat more tame type 2 algebra, where you can define a trace and density matrices. Now, once we have density matrices, we can define entropies. We define entropies in the usual way. The von Neumann entropy of a density matrix rho is defined as usual as minus the trace of rho log rho. So we've arrived at an abstract explanation of the fact that a renormalized entropy can be defined in the presence of gravity, at least for the particular example of an observer in a static patch of de Sitter space. So this rho can be the density matrix of any state in the Hilbert space, not necessarily the de Sitter state that we started with, for which the density matrix is the identity. So another way to say it is that rho could be any positive operator in the algebra of trace 1, just as in ordinary quantum mechanics. And we would have a definition of its entropy. We can show that for semi-classical states for which the usual generalized entropy can be defined, the von Neumann entropy of a state of the observer algebra does agree with the generalized entropy. So although I won't explain this proof today, we can recover the usual definition of the generalized entropy when it applies, but this definition generalizes the definition to what might be highly quantum states. Now I'm going to discuss a basic fact about mixed states in quantum mechanics. In ordinary quantum mechanics, a maximally mixed state has a density matrix that's a multiple of the identity, and it has the maximum possible value of the von Neumann entropy. The analog here is the state psi max with density matrix sigma max equals 1. It's clear that its entropy is 0 because the logarithm of 1 is 0. And by imitating an argument that in ordinary quantum mechanics proves that a maximally mixed state has maximum entropy, one can prove that every other density matrix rho other than 1 has strictly smaller entropy. So psi max is a state of maximal possible entropy. You might be unhappy with the fact that we define the entropy of the maximum entropy state to have entropy 0, because according to Gibbons and Hawking, the entropy is A over 4G. It goes back to the fact that there was a renormalization in the definition of the trace, which leads to an additive renormalization of the entropy. And in this presentation, there isn't enough microscopic knowledge to define the absolute constant in the entropy in a natural way. So I've simply defined it so that the maximum entropy state has entropy 0 and measured entropy is relative to that. We've learned that the system consisting of an observer in a static patch of de Sitter space has a state of maximum entropy that consists of empty de Sitter space with a thermal distribution of the observer energy. In fact, it was claimed long ago that empty de Sitter space has maximum entropy. The original argument was based purely on thermodynamic considerations with no microscopic definition of entropy. The idea was that the static patch becomes empty in the far future because particles, as de Sitter space expands exponentially, particles and fields leave the static patch. So the static patch spontaneously evolves to become empty. So if you believe there's a second law of thermodynamics, then since anything evolves to an empty static patch, the empty static patch must have maximum entropy. That was the original argument. We've recovered the result with the precise notion of entropy as the von Neumann entropy of a state of an algebra. To do that, we had to include an observer. But I actually think that's a feature rather than a bug. A criticism of well, I'm reluctant to criticize such a wonderful ahead of its time derivation, but a criticism of it could have been that beyond this classical approximation, it wasn't clear what static patch you're trying to talk about, or what you meant by the static patch. But here, since we've defined the static patch, and since what we really defined is the algebra of an observer, our discussion is clear, not just in the classical limit, but beyond that. So I think including the observer was technically needed for my derivation, but it also makes the statement much better defined. Now, what happens if we consider an observer in a more general spacetime? Well, if the observer can see a whole Cauchy hypersurface, then, well, analogy with results in ordinary quantum field theory strongly suggests that the observer algebra in this spacetime is simply the algebra of all operators on the Hilbert space of the theory, which technically is called a von Neumann algebra of type 1. So I'd expect that that's the answer whenever there are no horizons, cosmological horizons, that prevent the observer from seeing a complete Cauchy hypersurface. The more interesting case is an observer who, because of cosmological horizons, cannot see a whole Cauchy hypersurface. Of course, the notion of a horizon is tied to a semi-classical description in which we have classical notions of causality. I'd imagine, though, that in any description in which the notion of a horizon is precise, that an observer whose vision is limited by horizons cannot resolve quantum microstates. And thus, in such a case, the observer algebra will not be of type 1. On the other hand, if optimistically we assume that entropy can be defined by the observer in any spacetime, then the observer algebra should always be of type 2, and not type 3 as in the absence of gravity. So I'd hope that in the presence of horizons, we would always get a type 2 algebra. So remember, the observer algebra as an OPE algebra is defined universally, but as a von Neumann algebra, it depends on the Hilbert space it's acting on, and it could be of different types. And it can definitely be of type 1, but I would hope that in the presence of horizons, it will always be of type 2. Now here I should tell you just one fact about type 2 algebras. If the type 2 algebras have a trace, but there are two basic cases. If the trace of the identity operator is finite, we can rescale the trace so that the trace of the identity operator is 1. The algebra is then called a type 2-1 algebra. And as we've seen, it has a state of maximum entropy, namely the state whose density matrix is 1. If the trace of 1 is infinity, we can't normalize the trace that way. And with a little more detail, you can show that there's no natural way to normalize the trace because the algebra actually has an outer automorphism that rescales the trace. So the algebra simply does not have the information that would tell you how to normalize the trace. It turns out that in such a case, there's also no state of maximum entropy. The algebra is said to be of type 2 infinity. A simple case that leads to this is the algebra of operators outside the horizon of a short-shielded black hole, or a more general black hole as shown in one of the recent papers I cited at the beginning. that algebra is of type 2 infinity. And there it's obvious there shouldn't be a state of maximum entropy because you can keep putting more matter into the black hole and increasing its size and entropy. So you couldn't really expect a type 2-1 algebra in the presence of well, not of a Schwarzschild black hole in asymptotically flat space, for example. Anyway, when the trace of the identity is infinite, you get an algebra of type 2 infinity with no state of maximum entropy. Now, I expect that in a generic spacetime with horizons, the observer algebra is of type 2 infinity. One reason is that in a general spacetime, it's hard to imagine what could possibly be a maximum entropy state. So I imagine maximum entropy states are very scarce. But more specifically, you can actually see in some simple examples that the algebra is type 2 infinity. One example I like is the Schwarzschild de Sitter spacetime. So it contains a black hole, but you can make the entropy bigger by making the black hole smaller, because then the cosmological horizon grows and the entropy increases. If you try to maximize the entropy, you have to shrink the black hole down to a point. But when the black hole mass goes to 0, you have a singularity classically, and the topology of spacetime jumps. The topology of a spatial section in de Sitter is SD minus 1, but in Schwarzschild de Sitter, it's a circle times SD minus 2. And when you take the black hole mass to 0, there's a singularity, and the topology jumps. So in this example, when you try to find a maximum entropy state, you're led out of the region where classical field theory is good. You pass through a highly quantum singularity of some kind that we don't understand too well, and we expect you come out on the other side. Indeed, with the maximum entropy, a different space-time where now there is a maximum entropy state. So I suspect that's the general state of affairs. In trying to maximize the entropy in a general space-time, you'd end up passing through a topology-changing transition to a different space-time in which the entropy can be bigger. And maybe after a lot of such transitions, you'd end up in de Sitter space. But now I want to say something about comparing the different spacetimes. And of course, if we understood the topology changing transitions, we would use them to compare the different spacetimes. But I want to try to compare the different spacetimes without knowing how to do that. In the case of a type 2 infinity algebra, because there's no natural way to normalize the trace, there's also no natural way to fix an additive constant in the entropy. If I rescale the trace by e to the c for a real number c, then to satisfy the definition of a density matrix, I must rescale the density matrix by a reciprocal factor. And then you can see that the von Neumann entropy is shifted by a constant that's independent of rho. So if all you have are the algebraic relations of a type 2 infinity algebra, you can define entropy up to an additive constant, but you have no way to fix the additive constant. It's like classical physics where entropy is defined by relations like dE equals TdS, which determines entropy changes, but doesn't give you the zero of entropy, which in fact wasn't naturally defined until quantum mechanics came along. So there's an undetermined additive constant in the entropy in any spacetime where the observer has a type 2 infinity algebra. But do we have to allow a different additive constant for each spacetime? That would be highly unsatisfactory because then we could not compare entropies in different spacetimes. I believe one way to avoid this conclusion is to use the Hartle-Hawking no boundary state. It's a sort of gravitational version of the de Sitter state psi ds that was important in the de Sitter case. Remember, or hopefully you know that this, hopefully you know since I didn't have time to explain it, that the de Sitter state is taken. You want to define a state on a sphere, a spatial sphere. You take a hemisphere, which has the sphere as its boundary. A path integral in the hemisphere defines the state psi ds. Hartle and Hawking, but that's in the absence of gravity, so you could just pick the manifold, the hemisphere. In the presence of gravity, according to Hartle and Hawking, to do something analogous, you have to sum over all bulk manifolds with a given boundary. And the path integral over all bulk manifolds with a given boundary as a function of the boundary data defines the Hartle-Hawking no boundary state, which, as I've said, is a sort of gravitational version of the de Sitter state that was important in the de Sitter case. Now remember that in the de Sitter space, the maximum entropy state has maximum entropy, has density matrix 1, sorry. In de Sitter space, we have the state psi max built from psi ds. It had a density matrix 1 and maximum entropy. Because it has density matrix 1, we can reinterpret entropy as relative entropy with the maximum entropy state, where this is the usual definition of relative entropy. And you can see that since sigma max is 1, its logarithm is 0, and so this is a trivial identity. One thing that suggests to me that what I'm about to do is a good idea is that something similar was done by Aaron Wall when he proved the generalized second law. He reinterpreted entropy as relative entropy with the Hartle-Hawking state. And that led to a proof of the generalized second law. So I'm going to do the same thing with a different Hartle-Hawking state, the Hartle-Hawking no boundary state, a different Hartle-Hawking state, but a cousin. Now, you see, what do we gain by replacing this with this? What we gain is that, unlike entropy, the definition of relative entropy is invariant under rescaling the trace. If you rescale the trace, you have to rescale the density matrices, but the constant shifts that come from what happens to the logarithms cancel between the two terms. So relative entropy does not depend on the normalization of the trace. And that's related to the fact that relative entropy can be defined even in a type 3 algebra where there is no trace. So I suggest that the no boundary state psi HH is a universal maximum entropy state that sort of generalizes the well, what I called psi max to gravity. If so, then writing sigma HH for its density matrix, an improved definition of entropy for an observer in any closed universe is this one. And it's improved because it fixes the absolute constant. When the algebra is a type 2 infinity algebra, we wouldn't have known how to define this term by itself, but the difference is well defined. Since this does not depend on the normalization of the trace, entropy defined this way only has one arbitrary renormalization constant, independent of the spacetime. That constant is actually the logarithm of the norm squared of the Hartle-Hawking state. According to Gibbons and Hawking, well, maybe I should say according to Gibbons and Hawking and Hartle and Hawking, because I'm citing a paper of Gibbons and Hawking that preceded Hartle and Hawking, I think. But anyway, according to Hawking and his co-authors of the 70s, the logarithm of the norm squared of the Hartle-Hawking state is the entropy of the no boundary state. So they proposed that by analogy with things about black holes, but there wasn't a microscopic definition of entropy that made it true. I still don't have one. In my presentation, I can't justify interpreting this constant as an entropy. So in my presentation, I've just defined the entropy of the maximum entropy state to be 0 and measured all entropies relative to that. But at least that's enough so that we can compare entropies in different spacetimes. I think I'll stop here with only one further remark. Stephen Hawking famously said that the experience of an observer whose vision is bounded by horizons has to be described by a density matrix rather than a pure state. Now, it might be that this remark should only be interpreted as metaphor rather than something that's literally correct. But if you want it to be literally correct, then you should want the observer algebra to be always of type 2 whenever the observer vision is bounded by horizons. Thank you.
In the beginning of your talk, when you consider background independent associated to a worldline, is there a way to relate those background independent different worldlines?
Well, the algebra I defined was universal. It only depends on the laws of nature. So different spacetimes, well, it doesn't, sorry. When I say different spacetimes, it's really a pair, the spacetime and the embedding of the worldline in it. The worldline, when we had gravity, the worldline was a geodesic. It could be any geodesic according to the laws of nature. Without specifying the spacetime, it's not meaningful to say which geodesic it is. I didn't write down an action, a combined action for the bulk together with the observer. It would have been a bulk action such as the Einstein action. And then we'd have had an observer action, which would have been PQ dot minus MC squared minus Q times the square root of the metric along the world line. I'll call it E. And then By a space-time, I really mean something you get by finding a classical solution of that and then quantizing fields. So what I call a space-time is really a space-time with the geodesic in it, the geodesic being the solution for the observer world line. So when I said that the observer the algebra was universal, only depending on the laws of nature, and doesn't depend on the space-time, I should have specified it also doesn't depend on which particular geodesic is that world line of the observer. Well, it doesn't matter. We can go first.
Sure. So this universal algebra,
Yes.
You identified it later with one algebra and very simple.
Yes.
But do you mean that it's that you need to consider a specific weak closure of that in every given focus, or are there operators that are missing when you get the weak closure in the original algebra?
Well, the main thing that happens, but well, it's one of many things I left out of this talk to fit it into 35 minutes, is why I said that the algebra becomes much smaller when you have a Hilbert space representation. It becomes much smaller because, for example, suppose one of the fields is a free field. The commutator 5 tau times 5 tau prime is a C number. But which C number it is depends on the spacetime. And when we discuss universal relations, that's not one because it depends on the spacetime. So the algebra as I defined it would include elements representing the commutator of 5 tau with 5 tau prime for arbitrary tau and tau prime because there are no universal values for those. But in a particular spacetime, we wouldn't need that operator. We could replace it with something else. That's the main thing that happens when we go to a spacetime. The algebra becomes a lot smaller. But your question is, what do we do to get a von Neumann algebra? I kind of didn't want to go into what seemed like slightly extraneous details, but if we literally want to get a von Neumann algebra, we have to take bounded functions of these operators.
Yes. If I consider this observer as a quantum particle with some wave function, so in principle there is a finite probability of being anywhere. Does that mean like I don't have a sharp horizon and it becomes type 1?
Well, first of all, although I didn't go into enough detail to be entirely clear, we are considering it as a quantum operator. What we aren't doing though, okay, I perhaps at the beginning should have mentioned David Kolchmeyer's lecture Monday. He considered the case where the observer mass is so small that the observer is not well localized inside the horizon. As he explained, his story goes over to the much simpler picture I've explained. If the mass is much bigger than the de Sitter temperature. So I've taken an observer who's, to have a semi-classical picture, I assume that the observer is well localized on these scale in which the metric varies a lot. But we don't treat the observer classically. There are quantum fluctuations in the observer's motion. We construct this is a little bit schematic, but we take that action and quantize it and get a Hilbert space that describes jointly the space-time together with the observer in it. So the observer position is fluctuating just along with everything else. I expect the type of the algebra is determined though by whether there are horizons in the classical limit.
Also in the beginning, before you specialized to empty de Sitter space, I take it the formalism was really completely general, so it's not important the way that the world line has infinite affine length or proper length.
Well, this is a very important question. So Raphael is asking, what would we do, for example, in a Big Bang or a Big Crunch cosmology, where the observer world line doesn't go forever into the past or future? Or for that matter, if you're thinking of the lecture as being about a highly idealized version of us, our world line doesn't extend into infinite past. And well, it would be rather optimistic to claim it extends into the infinite future. Some of the discussion at the beginning made sense in general, but I only got something interesting because there was a shift symmetry along the observer world line. And we wouldn't really have that for a world line that begins or ends at a singularity. And so I don't have a nice extension of what I've said to that case. I'd prefer to know what one should say in that case, but I don't have a good answer.
I think we're describing observers that fall into black holes. So
Yes.
really connect.
Yes. I'd like to say something about them other than that their world line ends.
Is there any way to make the observer's spectrum discrete and maybe as a more microscopic picture? I assume that's somehow related to the semi-classical limit that you have a continuous spectrum.
I don't know, but I suspect if you want to do much better in modeling the observer, you might have to be much more realistic. A fun model of an observer used by, I think, Jeffers and Lampros, although I'm afraid of Lampros, was to model the observer as a black hole.
I'm wondering how large the Hilbert spaces you're considering for these spacetimes are. Well, not large as in this dimension of the Hilbert space. I mean, what kind of states you include. Earlier you started with the Bunch-Davies state in the quantum field, but then when you started talking about the Hartle-Hawking state, did you drastically enlarge that same?
When I talked about the Bunch-Davies state, I really meant the Hilbert space of quantum fields in de Sitter space. Sorry, I meant the Hilbert space that contains the Bunch-Davies state. You have quantum fields in de Sitter space. Once you assume a Hilbert space that contains the Bunch-Davies state, you can act on it with a lot of other states and make a whole Hilbert space, which I didn't want to spend the time describing today, but it's a construction that's been much discussed in the literature back to the 60s. So starting with the state I called psi ds is really the most efficient way to describe the de Sitter Hilbert space. But I didn't go into details. Then when I said we could define an entropy for any state, I meant any state in the Hilbert space you get by acting with quantum fields on the natural de Sitter state together with the state of the observer.
So sorry, to clarify, the Hartle-Hawking state is not in that Hilbert space?
Well, it's not. Well, if you include gravity, then the Bunch-Davies state is an approximation to the Hartle-Hawking state. It's an approximation on the grounds in the de Sitter state, you consider by definition only the hemisphere as a manifold whose boundary is the sphere. With gravity, you're supposed to sum over all possible manifolds. But inasmuch as Newton's constant is weak, it's believed that the dominant saddle point is the one that's used in constructing the state psi ds. So the Hartle-Hawking state in a limit goes over to the state psi ds. And I simply, at the end of my lecture, interpreted the Hartle-Hawking state, the no boundary state, as a maximum entropy state in a broader context.
There's a question on the Zoom.
If there's a question on the Zoom, you can unmute and ask.
Oh, hi. Thank you for the nice talk. Good. I was just I had a question about your previous slide where you talked about the fact that the entropy for mod psi Hartle-Hawking state squared is you say it's actually 0. So is this like some sort of canonical purification that you're saying that it should actually be 0 rather than a over 4g?
No, I'm not saying it that. In my presentation, the entropy of the Hartle-Hawking state was defined to be 0 because I can't do better. I believe the Gibbons-Hawking answer is correct, but it has the drawback that although the Gibbons-Hawking answer is presumably correct, it doesn't come from any real microscopic definition of entropy. I did the best I could with the microscopic definition of entropy, but I only was able to define entropy relative to the Hartle-Hawking state. So in my presentation, I'd say my presentation is missing something. The definition I gave of entropy is relative to the no boundary state may well be correct, but I'm missing the additional information you would need to define sensibly the entropy of the no boundary state. I just made explicit that that information is missing by declaring it to be 0, which, because there was no justification to say anything else in this lecture. And I wanted to make it clear actually that something is missing.
Right.
What
because
might be missing, for example, let me just comment quickly. Okay, we don't know a family of theories depending on an integer n that has semi-classical gravity in the large n limit and would give finite, well, at least type 1 algebras and all that, and well-defined entropies. But if you could approximate the discussion by some kind of n-dependent, more discrete theory, maybe, okay. If you can model de Sitter 3 space by double scale at SYK, as some authors have speculated, then without going to the double scaling limit, taking finite but very large n, you could, in that context, make sense of the zero of entropy. If you take the double scale limit, you have a type 2 algebra, and you wouldn't be able to do better than I said, and to find entropy relative to the maximum entropy state.
But I thought in the context of double scaled SYK, that's looking at static patch holography rather than the global de Sitter picture like we have in Hartle-Hawking, right? These are, I thought they're two distinguished entropies right there, because if I compute the entropy using the Euclidean path integral method for the Hartle-Hawking, I end up with something that goes as e to the plus s, and then with the static patch, it goes as e to the minus s, both being a over 4g. But those
What is it? I have to confess, I don't know what gives e to the minus s.
Oh, right. Oh, I was just saying that if I compute the Euclidean action for the static patch of de Sitter, then I end up with e to the minus s.
Oh, sorry, okay. Well, you see, I took the density matrix of the Hartle-Hawking state to be 1. But all I really, since I conjectured it was a maximum entropy state, all I should have really said is that it's a multiple of the identity. Now, if I'd wanted to get the Gibbons-Hawking answer, what I should have said is that the density matrix of the Hartle-Hawking state is psi hh squared. And then I would have gotten the right additive constant. Now, I didn't want to cheat that way because I can't justify it. But see, well, first of all, I think that Gibbons and Hawking saying that the path integral of de Sitter space can be interpreted as an entropy makes sense intuitively. And okay. Well, let me simply say that I think the Hartle-Hawking state has a natural normalization that comes from the path integral, but I didn't use that. I just removed it. If I hadn't removed it, I'd more or less have gotten the right answer, the Gibbons-Hawking answer. I removed it because I couldn't justify keeping it in a way that I was comfortable with. But that's what's missing in this presentation.
Because I was thinking back to your paper on quantum gravity and de Sitter space, where you define a new inner product, where you talk about scattering between scri minus and scri plus between a state and its CPT conjugate.
Yes.
Would that not then end up with you getting 0 for the entropy? Because this would be equivalent to canonical purification. Maybe that's
I don't know, but I'm skeptical that that paper had anything that's going to help us understand de Sitter entropy, to be honest.
Okay.
Okay,
Thank you.